be talking about joint work with Aztec, as reported in the preceding talk. So there's a quick summary of what we've been working on. So we have a voting solution on Ethereum. We assume we assume it's token-based, NFT-based, that is. We should have voter anonymity for life, essentially. And the votes themselves should be shielded for the duration of the voting period. And as much of this as possible should be verifiable on-chain. So let me talk a little bit about the high-level design. So from the front-end perspective, each prospective voter would acquire an NFT that would probably guarantee membership in some DAO, for example. And each prospective voter would enroll to vote only once by registering on a separate smart contract called the registry contract. This is for technical reasons that might become apparent a bit later on. Now, a voting process is created, and a call is made to some time lock service. So I won't go into too much detail about, but essentially it's a service that can give us verifiably random key generation, where you get a public key at some point in time, and you're guaranteed not to get the private key until some later point in time, and it is more or less trustless in the sense that a lot of parties are involved, some kind of threshold encryption, and assuming at least one participant is honest, then you should be good. And so votes come in, and at the end of the voting period, the private key is revealed. Anybody can compute the results, submit the results together with a ZK proof that everything was computed properly, and bam, maybe some on-chain action would be carried out afterward, depending on what the proposal was. And from the back-end perspective, for pretty much all the steps, starting from voting process creation, some computation is run on the user's machine, ZK proof generated, and that proof is submitted to a smart contract, which then verifies things. And if everything worked out, then something is stored in the smart contract or emitted as a log. So as a refresher to sort of go into a bit of detail about how all this is possible. So for Ethereum, blocks kind of look like this. So you've got this linked list model, and in each of these nodes, you have so-called state root. So all accounts, all contracts kind of live in this big tree, Merkle-Patricia trie, the state trie, and the hash of the root of that trie is stored in each block for that particular block number. Now, what you can do is, given a certain address, for example, the smart contract, like the registry contract I mentioned earlier, or maybe the NFT smart contract, you basically go down, starting from the root of the trie, you just kind of resolve that address more or less. I'm kind of sort of skimming over some details here, but you basically go one nibble at a time. So one, hex character at a time. And as you go along, you always make sure that Keccak hashes match up and so on until you get to the account you want, which would be NFT contract or registry smart contract. So this ends up being pretty expensive in the snark because A, Keccak, and B, actually decomposing things into, individual hex characters it's a bit of a pain. So in our case, we need this. We need to work our way down from the block. And then once we actually work our way down to one of these contracts, what we want to do is say, hey, this NFT with a certain ID actually is owned by this address. And we need to actually check that by starting from that account, that smart contract, which has yet another trie in it, the storage trie. And we need to work our way down to the NFT ID to show that it, is owned by an address. And then with the registry smart contract, it actually contains a public key that is associated to your wallet in some way, but doesn't coincide with the public key of your wallet. So this is the kind of stuff that happens under the hood. And now I'll get to the implementation. And the setup is, as I said, we have the Ethereum blockchain. We have some ERC-721 smart contract. We have some ZK Snark proving system. For us, this is Ultraplonk, basically through Noir, with underlying field BN254 scalar field with embedded curve baby jump for us. We should have the possibility of on-chain verification. So essentially, the concepts here can be moved to different settings because a lot of the primitives we use are available in CirCom. They're available Halo 2. So, none of this is specific to our setup, but there are some general principles going on under the hood. We assume given some ZK Snark friendly hash function. In our case, it's not exactly a hash function. It's basically Poseidon for some fixed, input length projected onto the first component. And then we have some compromise hash function that should be cheap enough to do in a snark, cheap enough to do in a smart contract. We've kind of gone with Poseidon again. We're having a think about it, but that's what we ended up with. And we assume that we have some kind of time lock service for basically hiding the votes during the voting period. This is something we're developing in parallel. So the contracts we have, like I said, we have this registry smart contract. It's pretty simple. Just takes an address to a public key, a baby jub public key in our case. Basically, we want a public key that's snark friendly. And essentially, we're going to end up plugging the private key of this into some circuits, and we don't want to plug in our Ethereum private key. And I mean, there are alternative ways of going about this, but this is kind of the approach we chose. We have this voting contract, which is where I guess most of the logic lives. So voting processes are created there. Relevant data for the voting process, like process number, maybe an IPFS link to the proposal, voting choices, period, time lock public key are stored in there, as well as an aggregation of the ballots. So as the ballots come in, we basically, and encrypted ballots that is, we basically plug them into this hash function and just kind of have like an aggregated hash of all the votes that have come in. Basically as a check at the end. Once the results are computed, we want to make sure the votes haven't been tampered with. So that's where that comes in. The results are also stored in there. The ballots themselves are logged, not stored. Otherwise, it'd cost a lot of money to store them in the smart contract. And we have some verifier smart contracts. So going to the various steps of the process. So voter registration is pretty easy. You just connect your wallet. You generate this baby jub private key by assigning a certain message and mapping it appropriately to a field. You compute the corresponding public key, and you submit that to this registry smart contract, which we call the ZK registry. The voting process creation, so here's where it starts getting a little bit more involved. So first off, you call out to that time lock service and say, hey, I need a public key. Private key should only be revealed at this later point in time. And then you need the voting parameters, obviously. But then you fix a block number. Should be the current block number, and you say, this is my census block. Everyone who has an NFT at this block number and has registered to vote, they are eligible to vote. Now, the thing is with those try-proofs I mentioned earlier, basically resolving, down to a contract or a storage slot, we don't have all that data on chain. So the next talk will actually talk a bit about that, about getting that kind of data. But essentially here, we need to provide that to the smart contract, but then you could provide, any old data to the smart contract. You wouldn't know that it's actually the storage root or the state root. So what do? You provide a ZK proof, essentially verifying that you have like the block as a blob and, the state root is in there. And you basically provide a succinct proof that all the data you provided is indeed what you claim it is. And so that's how the voting process is created. And then voting itself is, what involves basically signing your NFT ID together with the parameters of the voting process, signing your ballot or signing your vote, the vote itself, computing a nullifier from your, basically from your NFT ID together with the voting process parameters. This guarantees you do not double vote. And then what you do is you encrypt your vote by generating a one-time private key, and from that, computing a shared secret with the time block public-private key pair. And you use this to encrypt your ballots, and you fetch storage proofs that basically verify that you own the NFT you claim to own and that you are registered to vote. Now, you might say, well, okay, you have to do all this. You have to generate a ZK proof and submit all that to the smart contract, but then you're using your address, right? So people could actually see who voted. But no, it doesn't matter what address you vote from. So all of this stuff is address agnostic except for the registration. So it's assumed you use a separate account to actually submit this transaction. And at the end of the voting process, well, we have the time lock private key, and so we can decrypt all the ballots. We can, compute the results. We can compute, the aggregation of those ballots via that hash function. And if everything matches up, well, we submit everything to the smart contracts together with the proof, ZK proof that we've computed everything properly, and bam, the result will be stored and maybe some action will be carried out. So there are a few challenges and drawbacks here. So to actually get the data you need to prove you're eligible to vote, so those storage proofs, they don't come for free. So you need to actually call out to some Ethereum node to get that data. But in general, you can only expect to get the last, I don't know, M blocks of data from an arbitrary Ethereum node. So you need an archive node. But everybody uses Infura, so it's not really a problem, right? But we shouldn't rely on that. It is something to consider. Tri-proofs are very expensive to do in a snark, so lookups come in handy here to get things done, I guess, more efficiently in Noir, so with fewer constraints, but it is still quite heavy. The gas proofing cost balance is something to keep in mind. So generating these proofs is on the order of minutes rather than seconds. Gas costs are quite high for actually verifying these snark proofs. And of course, whale sightings are quite easy in this setting. So saving the whales is something to keep in mind. So there are ways around this by maybe coming up with a delay relayer. So that's also kind of on the roadmap to make it hard to correlate these votes, because it's one NFT, one vote. And so our outlook is, well, everything happens in the CLI with the CLI front end at the moment. So moving this to the browser would be ideal. And here we definitely need some form of recursion in order to deal with the large circuit sizes. And as I mentioned, a delay relayer optimization could be possible in some places. And as mentioned in the previous talk, integration is pretty tough at the moment. So that's somewhere we could definitely improve things. All this code is open source. It's all on GitHub, etc. And we have some posts on our blog detailing the stuff. So yeah, thank you for your attention.
Hello. Okay. You mentioned a time lock private key. Like, what is that about?
So in parallel, we have this service that calls out to we have this service that involves multiple parties doing a computation where you can essentially request a public-private key pair, but you don't get the private key until some later point in time. So this multi-party computation is, I guess, construed in such a way that it is quite impossible to actually get the private key without anybody colluding. If you want to read up on that, we actually use this service called DRAND. They also have like a time lock service in there. So in our case, we're building on their work by providing we have a separate blockchain which stores the data over time, and we allow you to obtain such public-private key pairs for a variety of schemes. And at the moment, it's just SecP256K1 and Baby Jub Jub. But yeah, if you look that up, you should find some information.
Document?